You know that feeling. You're staring at an oscilloscope screen, completely lost in this chaotic sea of ones and zeros. You're trying to diagnose a critical communication error on an automotive network, but honestly, all you see is an endless, jittery square wave. It's a massive pain point for so many of us. Without a structured way to read that raw bit stream, you're essentially trying to read a book in a language you don't even speak. Well, today, we're going to fix that. In this explainer, I'm giving you the exact tools you need. By the end of our time together, you're going to be able to confidently decode and understand standard CAN data frames right down to the individual bit level. We're strictly looking at the standard CAN protocol format here, translating all those dense specifications into clear, actionable knowledge you can actually use on the job. Okay, let's dive right into the core concept. To make sure you never forget the structure of a CAN frame, we're going to use a really specific visual analogy. I want you to think of a CAN frame not as invisible electrical pulses, but as a heavily regulated freight train moving down a single set of tracks. In this model, every single bit has a physical purpose. The very first bit, the start of frame, or SOF, is your arriving locomotive. It's a dominant 0 bit that aggressively announces the train is entering the station, shifting the entire bus from idle to active. Right behind that locomotive is the arbitration field. Think of this as the train's routing priority number. Because CAN allows any node to transmit, this 11-bit identifier ensures that the most important train always gets the right-of-way if two trains try to leave the station at the exact same time. Moving down the train, we hit the control field. You can think of this as the conductor's manifest. It details exactly how much cargo is on board. Next up is the data field itself. These are your actual cargo boxcars holding the critical payload. Following the cargo is the CRC field. This acts like a mathematical security seal, basically proving that no cargo was tampered with or corrupted during transit. And finally, we have the ACK slot, which is the receiving station's stamp of approval confirming the train arrived completely intact. Now, it's worth mentioning that not all trains are hauling cargo. It's absolutely crucial to understand the difference between the two main types of communication traffic here. A data frame is your standard freight train. It carries the actual cargo payload, which can be anywhere from 0 to 8 bytes of data. A remote frame, on the other hand, that's just a request. It's basically an empty train sent out to ask another node to send it its data. The key difference between the two is flagged by a single bit right after the identifier called the RTR bit. If it's dominant, you've got a data frame. If it's recessive, it's a remote frame requesting data. So that's the big picture analogy. But what about the strict math and the rules driving it all? Now that we have that visual anchor, let's transition into the actual numbers. The CAN standard specification is incredibly rigid, guys. There is zero room for interpretation or guesswork. We're breaking down exactly what makes up a standard frame. We start with 1 bit for the starter frame, 11 bits for the identifier, and 1 bit for the RTR. Then we have 6 bits for the control field, up to 64 bits for the data, a 15-bit CRC, a 1-bit CRC delimiter, a 1-bit ACK slot, a 1-bit ACK delimiter, and finally a 7-bit end of frame, followed by a 3-bit interframe space. We are strictly enforcing these exact bit lengths today. And just as a quick aside, the mathematical polynomial formula used to calculate that 15-bit CRC is complex enough to warrant its own separate deep dive, so we're going to consider that outside today's scope. Let's actually look a bit closer at that 6-bit control field. The first 2 bits, designated R0 and R1, are reserved bits for future protocol extensions. But the real magic happens in the next 4 bits, the DLC, or data length code. These 4 bits dictate your payload size. They're binary coded, meaning they can represent decimal values from 0 to 15. However, in standard CAN, this represents a payload of up to 8 bytes. So any binary value from 9 to 15 in standard CAN is simply interpreted as 8 bytes. Now, what's really interesting is how we actually apply this. Let's do a practical walkthrough. How do we take this theoretical standard and apply it to in the real world? Let's say you're probing a bus and you capture the start of a frame on your scope. You isolate the 11 bits immediately following the start of frame. Let's say you pulled this exact binary string, 00000010100. How do we turn that into a recognizable decimal identifier without losing our minds counting tiny squares? Well, every single position in this string simply maps to a power of 2, starting all the way from the right-hand side. Let's solve it methodically so no one gets lost. Step 1, we've isolated our 11 bits. Step 2, we map the powers of 2 from right to left. The furthest right is 2 to the power of 0, moving left all the way up to 2 to the power of 10. Step 3, we just look for where the ones are.
Reading from the right, the third position is a 1. That position is 2 to the power of 2, which equals 4. Moving a bit further left, the fifth position is also a 1. That position is 2 to the power of 4, which equals 16.
From there, we simply add those values together. 16 plus 4 gives us our final calculated decimal identifier of 20. By strictly following that position mapping, we've brought the theoretical math to a really satisfying, concrete conclusion. You've literally just manually decoded a CAN routing priority. But of course, it's not always that straightforward. There is a major trap you absolutely need to watch out for. Here's where things get super tricky. If you just count bits on a raw oscilloscope trace, your math is eventually going to fail. Why? Because of a major edge case known as bit stuffing. You see, CAN receivers need to stay perfectly synchronized with the transmitter at the bit level, so long stretches of an identical voltage level are incredibly dangerous. The receivers can literally lose their timing. To fix this, the CAN protocol automatically inserts a stuff bit. The rule is absolute. After 5 identical bits in a row, the transmitter automatically inserts a complementary opposite bit. This forces an electrical edge on the best, which allows all the receivers to resynchronize their internal clocks. This happens purely at the hardware level, between the start of frame and the end of the CRC field. And this brilliantly illustrates the exact trap I'm talking about. In theory, you have the data you think you're sending, 5 zeros. But in physical reality on the bus, we see something else entirely, 5 zeros followed by an automatically inserted 1. If you don't know the bit stuffing rule, you're going to count that inserted 1 as part of your data, or identifier, and your entire decoding process will be completely corrupted. The hardware receiver strips these stuff bits out before passing the data to the software, but on an oscilloscope, they are physically there, staring you right in the face. All right, let's wrap this all up with a quick survival guide. We've covered a ton of dense standard protocol material today, moving from high-level visual concepts right down to bit-level binary math. So let's do a rapid-fire recap of the absolute most critical takeaways. First, remember the freight train analogy. The start of frame is the locomotive, the identifier is the routing priority, the DLC is the manifest, and the payload is the cargo. Second, never forget the rigid rules of the protocol: an 11-bit ID, a 6-bit control field, and up to 8 bytes of data for a standard frame. And third, watch out for that bit stuffing gotcha. Every single time you see 5 bits of the same polarity on an oscilloscope, you need to know that the very next bit is a hardware-inserted synchronization pulse, not your actual data. By mastering these fundamentals, you transform that chaotic sea of ones and zeros back into readable, structured information. You're no longer guessing, you're decoding. If you found this breakdown helpful, hit subscribe to our YouTube channel Spectrum Speak for more EMC and automotive communication protocol survival guides. But before you go, I want you to think about this. If bit stuffing is silently altering your data stream at the hardware level just to keep clocks synchronized, what other invisible corrections is your transceiver making without even telling you? Until next time, keep your signals clean and your data frames intact.